big O variance and practice, omega, theta, tricky parts, and 3 problems. We've covered big O thoroughly, the language, the 6 classes, how to read it from code. This video closes the loop. We'll look at big O's siblings, big omega and big theta that you'll encounter in textbooks and interviews. We'll cover the tricky parts that trip people up, and we'll do 3 practice problems together. Data structures and algorithms foundations, big O variance and practice. A quick look back. Previously, we covered the 6 big O classes from O of 1 all the way up to O of 2 to the n. Each one defined, walked through with concrete examples compared at multiple input scales, plus how to read complexity straight from code using the 3-rule recipe. Today, 3 things. The siblings of big O, big omega, and big theta. The tricky parts that confuse people when they first try to read complexity, and 3 practice problems you can solve at a glance once we're done. The practice problems are the most important part. That's where the skill becomes automatic. Tricky parts, things that confuse people when they first try to read big O. I'm going to walk through 4 of these because they cover most of the mistakes I see in code review and interview answers. First tricky part, loop plus hash lookup, for x in R if x in scene. The scene lookup inside the loop is constant. Hash lookups are O of 1. So this is n iterations, each doing constant work. The total is O of n, not O of n squared. A common mistake is to assume loop inside loop body automatically means quadratic, not if the inner work is constant. Second tricky part, 2 sequential loops. For x in R, then later in the function for y in R. Both loops run in times. So that's O of n plus O of n, which equals O of 2n. The big O drops constants, so it's O of n. 2 passes is still linear. Add the complexities, then simplify. Third tricky part, recursion that doesn't branch. Like def of n returns f of n minus 1 if n greater than 0, else 0. 1 recursive call per step, n levels deep. That's O of n. Not exponential, only branching recursion with 2 or more recursive calls per step is exponential. A common mistake is to assume any recursion is dangerous. Linear recursion is fine. Watch for branches. Fourth tricky part, nested loops over different things. For E in R, for J in matrix at E, the outer loop is over R, size n. But the inner loop is over a row of a matrix whose size depends on the data. So you can't just say n squared. The proper complexity is O of total elements visited across all rows. Sometimes that's linear, sometimes much more. Read what the inner loop iterates over before declaring n squared. When do constants actually matter? Big O officially ignores them. But there are cases, important practical ones, where the constants determine which algorithm to use. So when does big O lie? Rule of thumb, at n less than about 20, constants often dominate. At n greater than about 50, the big O class always wins. In between is fuzzy, depends on the constants, the cache behavior, and the implementation language. So if your inputs are always tiny, the big O class might matter less than the constants. If your inputs ever get large, the big O class is everything. Here's a concrete example. Python's built-in sorted function uses insertion sort below n equals 64, then switches to merge sort above. Why? Insertion sort is O of n squared in theory, but with very small constants. Merge sort is O of n log n, but with bigger constants and more memory allocation. At tiny inputs, the constants win, and insertion sort is genuinely faster. At large inputs, big O takes over and merge sort dominates. The Python implementation literally switches algorithms based on input size. Real engineering decision captured in one line of CPython source. Now let's talk about big O's siblings. Big O is one of 3 sibling notations that all describe the same idea, how a function grows with its input. Same idea, different bounds. You'll see all 3 in textbooks and in academic papers, so it's worth knowing what each one means. Big O, written with the capital letter O, is the upper bound. The worst case. We say a function is O of f when it grows at most as fast as f. The function might be faster on some inputs, but never slower than the big O bound. This is what we've been computing all along. Big omega, written with the Greek capital letter omega, the horseshoe shape. It's the lower bound, the best case. We say a function is omega of f when it grows at least as fast as f. The function is never faster than its omega bound, but might be slower on some inputs. Big theta, written with the Greek capital letter theta, is the tight bound. Both bounds match. We say a function is theta of f when it's both O of f and omega of f. Same growth from above and below. The exact growth rate. Why do we focus on big O in practice? Because production code is judged by its worst case. The hash set lookup that's usually O of 1 but O of n on a hash collision. What matters is the O of n. That's the case that bites you when traffic spikes. Engineers want to know, how bad can this get? That's the big O question. Best case is for textbooks. Worst case is for production. So big O wins in engineering practice. Practice, question 1. Read this code. Has 0 of r, a for loop over r. If we find a 0, return true. After the loop, return false. What's the big O? Pause the video right now and think about it for 10 seconds. Don't just guess, work through the logic. The answer is O of n. Linear time. Let's walk through why. We have a single loop. By rule 1 of our recipe, one loop equals 1 factor of n. So we're either O of n or simpler. Now there's an early exit. We could return true on the very first iteration if the first item is 0. So why isn't this O of 1? Because big O is the worst case. If no zeros exist anywhere in the array, we scan all n elements. The worst case is full scan. Linear, the early exit optimization, helps in practice sometimes, but it doesn't change the worst case complexity. Practice question 2. Has duplicate of R, 2 nested loops. The outer over the array from index I, the inner from E plus 1 to the end, comparing R at I to R at J. Returns true if any pair matches, otherwise false. What's the big O? Pause and think. This one has a subtle wrinkle. The answer is O of n squared. Quadratic time. Let's walk through it. Apply rule 1. 2 nested loops over the input. The outer loop runs n times. The inner loop starts at I plus 1, so it runs n minus I times. Total comparisons sum to roughly n squared over 2. That's where the wrinkle is. It's not exactly n squared, it's n squared over 2. But big O drops the 1/2 constant, so the answer is still O of n squared. The subtle wrinkle doesn't change the class, just changes the constant. And constants don't matter to big O. Practice question 3. Looks like a classical implementation. Low and high pointers, mid calculated as the average, narrow the range each iteration based on comparison. Assume the input array is sorted. What's the big O? Pause and think. This one tests pattern recognition. What familiar algorithm is this? The answer is O of log n. Logarithmic time. This is binary search. Apply rule 2. Each iteration halves the search range. The loop runs log base 2 of n times until low crosses high. Binary search is the canonical halving algorithm. Whenever you see a while loop where the range is being divided by 2 each step, it's almost always logarithmic. Remember the very first hook of this series way back in the a priori analysis video? 2 functions, same problem, find duplicates. Same correctness, one finishes in seconds. The other takes longer than is practical at 1,000,000 items. Now we can see exactly why. Version A is a nested loop, O of n squared. At n equal 1,000,000, that's 10 to the 12 operations. Version B is the lookup trick hash set pass, O of n. At n equal 1,000,000, that's 10 to the 6 operations. Same correctness, 1,000,000 times the work. You can now see this without running it. That skill, reading big O straight from code, is the entire skill this series has been building toward. This is the core idea. You don't need to measure seconds. You don't need to benchmark. You don't need profilers or load tests or any of the other tools engineers reach for when code is slow. You just look at the code and ask one question, as in doubles, what does this loop do? If the work doubles, you're linear. If the work quadruples, you're quadratic. If the work stays the same, you're constant. If the work explodes, you're exponential and you need to refactor. That's big O, that's the core idea. Master that one question and you'll catch most performance problems before release. Here's where we are in the series. We've come a long way. Previously, algorithms, a priori analysis, big O notation, the 6 big O classes, and reading complexity straight from code. The core toolkit for time complexity. This video, Omega, Theta, tricky parts, and 3 practice problems you can now solve at a glance. The complete picture for time complexity. Coming up, space complexity, the other dimension of complexity, because a function can be fast and still run out of memory, and most engineers think about space only when they need to. Worth your attention? Simplicity is prerequisite for reliability. Dijkstra. The lesson, clean big O analysis, comes from clean code. If you can't quickly tell what the complexity is, your code is probably too tangled. Simplify until the complexity becomes obvious. Then both your code and your analysis improve together. Thanks for watching. If this video helped you understand big O variance and tighten up your code reading skills, please like, subscribe, and leave a comment below. Tell me which practice question caught you off guard. More on space complexity and algorithm design is coming in future episodes in this playlist. See you there.